Hello and welcome to the Daily Space for today, Thursday, June 25th, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Today's news is less straightforward than normal, and we're going to cover two of the many news stories coming out today because we want to get this right. We'll be doing a lot more news tomorrow, so don't worry, nothing's going to get left out. We're just spreading it out so that we can really make sure you understand today's news. Both stories are related to the detection of gravitational wave events and are believed to be caused by the merger of massive objects far off in the universe. When we observe the universe, we can perceive events in three different ways. We observe light that events may produce. Stars shine. Gas clouds emit radio waves. We can potentially detect any particles events send our way, for instance, neutrinos. And we also look for the way gravitational pulls change the shape of space. This final way we see the universe generally just means we look at how the paths of light and the motions of objects change near high mass objects. But sometimes we can actually detect waves of gravity propagating through the universe in the form of gravitational waves. A large mass object hanging out alone in the universe deforms the space around it. But that is about it. Now put that large mass into orbit with another large mass, and as they move, they are creating moving deformities in space-time, generating waves that carry energy away from the system. This was all predicted by Einstein in 1916, and we've known that gravitational waves exist since the 1970s, when we could see how the energy gravitational waves carried away was changing the orbits of binary pulsars. This confirmation via indirect methods spurred on dreams of directly detecting gravitational waves from the distortions they create in space-time. Now, we're not talking about figurative distortions. We're talking about literal, where things get stretched and compressed as these waves ripple through space, distortions in space-time. One of the most accurate means we have for measuring changes in distance is actually light. The wavelengths of light can be smaller than the size of an atom, and light can only interfere when waves combine in integer and half-integer combinations that cause the light waves to either amplify or cancel one another out. The patterns of waves going through slits and then interfering with one another can easily be measured. And you can even generate a simple interference pattern just by bouncing laser light off the surface of a CD and seeing a series of red dots on a wall that mark out the places where light combines constructively. With gravitational wave detectors, laser beams are shined over great distances down tunnels that are at right angles to each other, and that light is combined in ways that allow the slightest change in length of these tunnels to be detected. By scattering multiple detectors around the world, it becomes possible to measure the effects of gravitational waves as they propagate through our planet, deforming everything as they travel at the speed of light. By looking to see when different detectors are deformed, we can follow the path of the wave and then work backwards to localize its origin very roughly in the sky. In one very dramatic case, gamma ray 2017-0817, the merger of two neutron stars was detected not just in gravitational waves, but also in particles and light as it went off during a merger. Gravitational wave detections are finally starting to become rather standard, with new events being captured on a regular basis. And these detections are now being announced in real time to allow more and more people to try and get follow-up observations of, well, anything that may be associated with the events releasing the waves. This means these events generally aren't news, except for today, apparently. Now, so far, the majority of published results have been of objects of fairly similar masses. And, well, those are fairly boring situations. The similar masses are just a fluke of how star systems form. In general, stars and binary systems aren't too different in mass. And it's only when you start to get to triple systems and systems that you see forming. I apologize for the dog barking in the background. Um, these are what happen when you record at home. Um, so as I was saying, it's only in triple systems that you start to see things forming in very different sizes. Now, there's exceptions. There are always exceptions. But we expect things to not be too radically different on the high mass side of things. In high density environments, however, you can end up with binary systems forming late in the star's lives as the objects interact in their orbits. In April of 2019, a binary star system of extremely unequal masses was detected merging in a galaxy some 800 million light years away. The more massive object was a fairly common 23 solar mass black hole, but the smaller object is estimated to be about 2.6 solar masses. And no one is completely sure if that 2.6 solar mass object is a neutron star or a black hole. So far, the smallest black holes we found are around 5 solar masses, and the largest neutron stars we found are no more than 2.5 solar masses. That 2.6 solar mass object should be a black hole, but we're just not quite sure. Neutron stars are, to first order, supported from collapse under their own gravity by the pressure of neutron degenerate gas. This is the stuff the star is made of. It's literally a gas of neutrons. The particles are literally pushing each other apart just enough to hold the star up. Now, neutron stars can't support unlimited force. And at a certain point, the neutron's pressure will get overwhelmed and the object will collapse into a black hole. And we can't even speculate at what goes on inside of a black hole. The point at which a neutron degenerate pressure can no longer support a star occurs somewhere around 2.5 solar masses. But secondary effects like spin and irregularities in composition and other stuff can all affect that limit. So it's possible a 2.6 solar mass object is a neutron star. But probably not. But we don't know. So this could be the smallest black hole ever detected, and it was detected in the moment of its death. If we can get black holes this small now, the question becomes, why haven't we seen this small a black hole before? The answer may be as simple as it's harder to find small black holes, or they really are rare, or both. Whatever this object is, it is gone, merged into that 23 solar mass object to form a new and greater black hole than was there before. And now we're left wondering, exactly what was it that went merge in the night? Now, most black hole mergers occur in darkness. Literally, the events just don't emit any light. At least not generally. Several years ago, theorists predicted that if a black hole merger occurs in the heart of a galaxy, the merger of the two black holes under the gravitational influence of a supermassive black hole can cause the resulting merged black hole to fly out of the heart of the galaxy and into the surrounding material. This rapid exit can cause the material being plowed through to light up. And now, an example of this kind of a black hole making things light up seems to have been found. In May of 2019, a gravitational... I apologize for the problems we are suddenly encountering I'm just going to get rid of our slides. Today is a day of technological issues, it appears. I'm not at all sure how I got remotely logged out, but it has happened. So we're just going to continue on. All right. So, yeah. In May of 2019, a gravitational wave detection was made in the direction of the quasar 1249 plus 3449. Now, I haven't been able to find the ratio of the masses that merged, but the resulting new black hole is 100 solar masses. Now, several days after this merger was detected, the Zwicky Transient Factory detected a flare up in light that didn't match a supernova. In a new paper in Physical Review Letters, a team led by Matthew Graham describes how this 1-2 punch of observations, first of the gravitational waves and then of the flare up several days later, matches the earlier predictions of, well, a merger too close to a supermassive black hole that leads to a runaway black hole and a flash of light. This is a quote from the press release. At the center of most galaxies lurks a supermassive black hole. It's surrounded by a swarm of stars and dead stars, including black holes. This is according to co-author K.E. Savick-Ford of the City University of New York. Now, these objects swarm like angry bees around the monstrous queen bee at the center. They can briefly find gravitational partners and pair up, but usually lose their partners quickly to the mad dance. But in a supermassive black hole's disk, the flowing gas converts the mosh pit of the swarm to a classical minuet, organizing the black holes so they can pair up. That is one heck of a cool quote. And basically it's saying, look, there's black holes lurking in the centers of galaxies. Sometimes they get close enough and interact enough to form a new binary, and those binaries can merge. And then they just get kicked out under the influence of that supermassive black hole. So the theorists got it right. And now we know we need to be wary of runaway black holes because really, they are a thing. There's a lot more to this story, but we're going to end it here. And I'm going to ask Matthew Graham to come on and be a guest. So stay tuned, and we're going to talk to the people behind this amazing discovery of observations matching theory. But for now, that's all we've got. Thank you for watching. This has been The Daily Space.